So, hi everybody. I'm Carol Payne. Thanks for the intro, Emily. That's quite the intro. I feel like I do too much, but I'm here to talk to you guys today about something that you may not have heard from me before, and that is OpenVPCal. And let's see. Oh, gosh, this is going to be hard. So, all right. OpenVPCal, it's an LED-based in-camera visual effects calibration framework. It's a lot of words for stuff that you all have probably seen in a lot of capacities in your various work as you go through your day. When we started to look at this problem, we realized that LED-based in-camera visual effects, it's relatively new, give or take like the state of our industry overall. And while it's full of opportunities for innovation and creativity, it lacks standardization and repeatability, which are both, from my work as a color scientist, foundational aspects for an imaging workflow. You got to be able to standardize it and repeat it and make everybody see the same thing all the time. This presentation will focus on LED-based to camera capture specific color calibration and rendition issues, and our proposed solution, which again, we call OpenVPCal for now because it needed a name. Please note that this tool was developed and designed with today's problems in mind, and we really hope that future technology renders it unnecessary. I know it's a weird thing to say, but the work that this tool does is due to specific technology limitations that we need on sets on production today. So we also recognize that there are currently many specific and proprietary solutions to these issues, and we want to recognize that all of them have merit. What we realized, though, is that most share a common core workflow. So as is common in a lot of open source software, if we could standardize around those bits of common core workflows, and then more advanced workflows and specific solutions could build on top of it, then we wouldn't have to redo work all the time. So, oops. We're all familiar with the traditional scene-to-display pipeline, taking what was shot, the scene photometric values as recorded by the camera, and outputting them to a specific display specification in a perceptually equal way. We know this as tone mapping. However, in the context of an in-camera visual effects workflow, LED panels are light sources. So if LED panels are lights and not displays, what does that mean? First, current cinema camera technology varies between manufacturers and is often tuned to capture more wider band emissions, sunlight, memory colors versus the narrow bands of RGB LED lights. And then it also means that standard scene-to-display imaging pipelines and calibration techniques don't match in-camera visual effects needs. Tone mapping is counterintuitive here. We want to send linear light to these panels as that's what the camera is designed to see. All of these limitations are exacerbated by something we call in the color science world metameric failure. Modern digital cameras can't exactly capture colors the same way our human visual system processes color. While this failure exists under all light sources, it's more evident under RGB narrowband light sources such as LED panels used for video walls. And for both, in addition to metamerism, the other problems often encountered in the imaging pipeline is issues with linearity. This baseline, like we said in the previous slide, you want linearly encoded light emitted from the LED panels. And creatively, as you can see on the two images on the left, it's super important for the screens to respond similarly to physical light on set. Technically, as we'll discuss later, analyzing and correcting the EOTF, more acronyms for electro-optical transfer function, which is another word for a gamma curve or a PQ curve, is fundamental to a correct LED to camera calibration. All of these issues and more lead to unpredictable results, frustration, and friction between creatives and technology. So what did we do? Well, at Netflix, we decided to look at the whole kind of picture, and as we went through that discussion, we realized it's never just one thing. So we want to recognize that the topic of OpenVPCal is just one part of a larger workflow to produce an accurate, well-executed in-camera visual effects production. But you also have to start somewhere. So we decided to tackle the problem of calibration of the wall based on your primary camera capture first, because if what you're capturing on your primary camera isn't correct, nothing else downstream will work. The calibration system needed to reduce image artifacts and improve blending between physical and virtual sets, all in order to match creative expectations and get closer to that awesome goal of in-camera final pixels. At the end of this process, the color you send to the screen should be the color captured by the camera once it's properly calibrated. We had a few technical goals and system constraints to operate under. The first one being to reduce that metameric failure between camera and LED wall with non-destructive and repeatable color transforms, because there's lots of ways to solve this problem, but not a lot of ways to do it in such that you don't damage the image that's being captured, or you make sure you don't limit the ability to repeat it downstream. We need it to be easily deployable without any specific calibration equipment. We recognize, if there are any other color scientists in the room, that it's not ideal to use a camera as a colorimeter. It isn't one. But the barrier of bringing more equipment to set and its cost is too high for most productions to be practical. We need the tool to be flexible enough to be pipeline agnostic, fast enough to be run between takes on set without taking up time, and reliable enough to work for any camera and lens and panel and processor setup that you throw at it. The OpenVPCal workflow relies on the creation of target-defined calibration patches which you capture using your primary capture camera. Once that's done, you run the analysis tool, which creates a config containing the resulting calibration transforms. You can then play back your capture patches plus the calibration config and verify the results. Sounds pretty simple, right? Not so much. We're going to talk a little bit about the details around the calibration analysis. We have a number of color transforms within the tool, which are chained together in a specific order, though a user can enable and disable any of these phases should they not be needed in your workflow. The first is a per channel 1D LUT correction. The second is a 3x3 matrix to calibrate the RGB primaries of the LED wall. And the third is a gamut compression algorithm to avoid some color clipping depending on the gamut of your content versus your screens. The main issue at stake here, like we talked about before, is this camera Metameric failure and any potential issue caused by the content playback pipeline. Many different combinations of media players, image processors, and LED panels leave lots of potential for color artifacts or mistakes. So even if your camera was a perfect colorimeter and LED panels had perfect linearity, which doesn't happen, we would still have to address other potential issues from sources such as the content itself, or your processor, or something is impacting external light on the set that you want to compensate for. There's a never-ending list of problems that are always going to require a calibration and someone looking at these images. So we'll talk about a couple of these operations, or these three operations, a little bit more in detail, and I'm going to speed through a little bit of this. If you have more questions about exactly what we're doing, there's a contact email at the end of this presentation where you can get in on the beta test, because I know I'm speeding through this quite a lot. So the 3x3 color matrix, pretty simple. Designed to map the perceived color space of the LED wall as recorded by the camera to the target color space of the calibration, and to address any color mapping issues within the content to LED pipeline. So the 3x3 matrix can be used to map a standard color space such as Rec 2020 or P3, or to any custom color space such as the native LED primaries, which is a pretty common part of this workflow. In order to calculate the 3x3 matrix, it's pretty simple. Project the red, green, and blue patches on the LED wall. We record and measure the colors, and then we map the matrix, generate a color matrix to map the extracted color space to the intended color target. Basic 3x3 matrix. However, a hint here that as we were doing all this research that we discovered is that peak red, green, and blue, not the same on all panels, not the same as captured on any camera. So we actually used desaturated patches as we were getting tons of false readings, red not being red that we expected it to be, blue not being blue. We use about 70% saturated patches. You can see a couple of these issues here, a lot of it is due to the narrowband emissions of the RGB LED panels and the image processor internal calibration, as well as the cameras. So all of these things add up to not being able to predict peak red, green, and blue, which is the primary goal of most calibration systems. You can see here a couple examples of when we got data from these tests mapped in these images here. It's kind of hard to see. These lines help a little bit. 3 examples on the left is a hard clip on the green channel. At the center, it's like a bending of the red channel towards the edges of the gamut. And on the right, a full nonlinear path from white to full saturation in 2 of the 3 channels. And again, we're not picking on anybody here. This happens in all cameras, on all panels, and all image processors. Every one is different. None of them are perfect. So secondly, we also needed to correct the EOTF, your linearity of your panels. We do this by a series of per channel 1D LUTs. And as explained before, nonlinearity can cause issues in the resulting images projected on the wall in its contrast and color, as well as other complexities. So we generate these per channel 1D LUTs by measuring a known number of gray patches that go from black to white, weighted towards low light values. Low light in LED in-camera visual effects workflows is quite challenging. So when we were working through this, we added an algorithm to actually purge some of the readings in low light to avoid overcompensating correction in these 1D LUTs, because as you can see in this log-to-log plot, camera's noise floor, in addition to flare and other issues, make things behave differently when approaching black. And this is not only due to the cameras. You can see in this super scientific picture of my colleague's hand here against this panel, the LED panel itself is not helping. So, why is EOTF correction important? I keep hammering this point home. As mentioned multiple times, the LED output must be linear for in-camera visual effects. Not starting from this overall baseline is setting your workflow up for failure. So, another reason why this is important is 3x3 matrices are linear color corrections. So if you don't start from a place where your LED panel is outputting linear light and you're calculating this 3x3 matrix using it to correct your camera's color primaries, you're already starting from an incorrect place. And we actually saw that these artifacts can be quite significant. And here's an example of one that, this isn't an ideal scenario. It's from a less than maybe amazing image processor and LED setup, but you can see that there's quite a big difference between what the linear should be and what the EOTF captured. And it actually amounts to a decent amount of brightness difference, in this case about 200 nits of actual light emission difference in the highlights. You can also see that's not only brightness, but in color. Here's from a couple different cameras of how the different cameras see gray patches projected to the same wall with a different color cast, especially in the shadows. So like I said before, is if we're not balancing these channels from these desaturated patches and it's all inconsistent, we're going to start from that bad place and generate that wrong 3x3 matrix. So the EOTF correction in our pipeline happens first. The LED RGB primary correction happens second, and then the gamut compression is the last thing I'm going to talk about here. And it's just to avoid color clipping after this gamut mapping. So you do this primary correction, and there's a possibility that when you move these primaries around, you're going to move these primaries around outside of what your LED wall is capable of producing or your camera is capable of capturing. So we actually are using the ACES published gamut compression, but in a parametric way. So we're giving it its own parameters based on the LED wall and camera's capabilities, calculating those out of gamut colors, and we're actually compressing up to 10% of the color space, but that's also definable in the tool, depending on what you're doing. So the reasons for this, as can sort of be seen in this graphic, this GIF, is it playing? Okay, good. You'll see it more if you rely on a standard color space such as Rec 2020 or P3 and you're moving these primaries around. You'll see it less if you're able to rely on your LED wall native primaries. But not all productions have the ability to have, an imaging scientist on hand and someone knows how to get images back and forth from those native primaries and how to view that correctly and how to make sure that that all happens correctly on a set. So people default to P3 or Rec 2020, something that's standard and can go through all systems and stay exactly the same. That's where the gamut compression really comes in handy. And the last bit of this that is we're interested in feedback from the foundation on and from all you people that work in open source in the room is that as we continue to use and experiment with the first version of OpenVPCal, and we talked to some partners about it, it became clear that having a version that could be used consistently in all applications, including Nuke, our first version, this presentation doesn't mention it, but was done, our first version was done in Nuke with a Python API backend. That's its current stent. That's what it is in beta. We use Nuke because, as we all know and love, it's really easy and flexible to build prototypes and MVPs in that product and make it what we want and be able to have a UI on top of the framework that we use. But we also know that we want to be able to use it in any kind of circumstance that you have in your pipeline and for it to be flexible and extensible in that way. So we partnered with an incredible Netflix engineer. I'm not sure if he's listening today, but if you are, hi, Daniel Heckenberg. He built an independent extensible Python API. So we're still using Nuke for patch generation and UI UX integration, but the main calculations are now fully Pythonic. We were able to simplify considerably and also integrate a test framework to verify and check results. And also by using Python, we can make use of other existing libraries, such as OpenColor.io, which I'm a little biased to, and also Color Science for Python, and not redo a bunch of work that already exists. So with Python being the most widely used scripting language, we hope that all of you would be able to jump in and understand it pretty quickly. That's why we chose Python. Be easier to incorporate into existing workflows, tools, and pipelines. So as far as the OCIO part of this, in OCIO 2.1 and above, all OpenVPCal transforms can be expressed within the config using built-in transforms and color spaces, including the ACES gamut compression. Originally, we'd planned to support different iterations of OCIO versions, but as this development has gone on and a lot of applications actually now support higher OpenColor.io versions, specifically Unreal and Nuke and those applications we needed to run it in, most in-camera visual effects applications, they're already running OCIO 2.1 in the latest versions of those software. So we decided that we are going to support OCIO config generation for OpenVPCal for 2.1 and above, and fully encapsulated 3D LUT export for pretty much everything else. For any pipelines which do use a 3D LUT, we apply pre and post shaper conversions to that LUT, so you don't have to worry about losing data, integer conversion, all that stuff. So in conclusion, like I said at the beginning of this presentation, there's already a large number of very valid tools and workflows to calibrate LED walls today. They're really pretty similar to what we do here. So it's not rocket science. Why are we doing this? How hard can it be? We've been doing this project for like a year and a half now-ish, maybe a little bit longer. Run a lot of tests, lots of different production scenarios, put it through its paces in a bunch of different ways. It's in a closed beta test right now. And what we discovered is that it's really all the bits and pieces of this framework and the how to hook them together that makes this useful. We're not saying the work necessarily, the color science that we're doing is novel, but the framework that you build around it and how you integrate it is what makes this easy to use and deploy on a production. And that's really what we've been focusing on with this set of tools. So they're simple algorithms, but really important. And we've seen examples of how they improve the quality of life on set in a virtual production and camera visual effects workflow. So I think that's about it. I'd like to say a huge shout out to my co-lead on this project, Francesco Girardello. He's based out of our Netflix London office, and he would usually be here presenting half of this presentation with me. So I want to say a huge thanks to him and the rest of the people on this slide. Adrian Puello at Orca Studios is our Nuke developer, and again, a big thanks to Daniel Heckenberg on the Python side. And I think that that's it. This is the email for our beta test. We're in a closed beta, so that's why you maybe haven't heard. We're not putting this publicly out anywhere, but if you'd like a copy of the Python API to mess around with and give us feedback on, that's the price for being in the closed beta, is we're requiring you to give us feedback on it. So thanks a lot for your time.